Ladies and gentlemen, good morning for most of you, good afternoon for some of you. I would like to welcome you to our latest webinar in the series, Scientists Empowering Scientists of Single Channels, Postsynaptic Events in Virtual Signals. My name is Jan Dolzer here at ZF Instrument. Let me start by introducing the other speakers though. I'm very pleased to welcome a user as a speaker, Angela Snyder. She got her bachelor degrees in neuroscience and psychology at the Cedar Crest College in Allentown, Pennsylvania in 2015. Did an internship at the National Institute on Drug Abuse and joined UNC Chapel Hill, Dr. Lisa Tarantino's lab as a research technician between 2015 and 2016. And since 2016, she's working on her graduate degree in Yuval Silberman's lab in Hershey, Pennsylvania at the Penn State College of Medicine. The last speaker today will be Telega Atsaptos, who graduated at the Queens College in New York doing computer science, and in '87, the same year, joined Instrutech Corporation in various roles, in the end as the general manager, until Instrutech was acquired by Hika Instruments in 2007, and then until 2015, he was the general manager there at the Hika US division. And since 2015, I have the pleasure and the honor to call Telly my colleague here at ZF Instrument, where he works in technical support and, very importantly, also in product development. Myself, I graduated in Marburg, Germany, doing electrophysiology with insect sensilla, and during that time I already started consulting with Axon Instruments for a number of years. And in 2003, Axon Instruments hired me and relocated me to California. I stayed on through several mergers until 2011, when I went to ZF Instrument, leaving electrophysiology for a year and a half to be the product manager for laser-based micropipette pullers. I went back to electrophysiology, patch clamp electrophysiology, to Hika Electronic between 2012 and 2014, and then rejoined ZF Instrument as the product manager for patch clamp systems, a position that I hold to the present day. The agenda for today. I'm already in the middle of the introductory remarks. I'll spend 2 or 3 more slides on housekeeping items, and then we'll give a brief talk about single-channel analysis with ZF-Patch software. Then Angela will talk about analysis of spontaneous excitatory and inhibitory postsynaptic currents and action potentials. And then Telly will talk about the reality of virtual signals, nothing to do with virtual reality, even though, of course, the pun in the title, I assume, is intended. We will have a Q&A session in the end, and then you will be routed to a quick survey. That's only 5 questions, mostly about, did this webinar make sense for you? It's important for us to understand, was it useful at all? How did the timing work out? We realized there's obviously no one time zone that works worldwide, and also whether you want to still get in touch with you. So please take the time to fill out this quick survey. That's really important feedback for us to know what did we do right, but also almost more importantly, what did we do wrong? What can we do better next time? If you have not gotten audio yet, then these slides may be helpful for you if you do not have a computer that's equipped with speakers, or if you do not hear any announcements, dial in at one of these numbers. The access code is down here, and I will leave that up for another 10 seconds or so in case somebody has trouble hearing us. And then move on to the questions. In the session control panel, which by default should be on the right of your screen, you have a Q&A section where you can type questions. Please use the questions, not the chat, because otherwise it gets too complicated. And please mention which speaker your question is directed to. Sometimes that's obvious, but we don't want to have to guess about that. And all questions will be addressed either during the Q&A session at the end of the webinar, or if there are too many questions and we don't get to addressing them all, we will get back to you offline by email. We have a number of documentation materials. We have 3 PDFs, which in essence represent the slide decks of the 3 speakers. You can download them through the webinar control panel. A video recording of the webinar will also be available on our YouTube channel, and we usually do that within 2 weeks. And everybody who was registered for this webinar, even those of you who were unable to make it today, will receive a notification by email when the recording is online. Now let me switch to my talk. The title of my talk is Single Channel Analysis with Certipatch software, but before you can analyze single channels, you need to record them. So I want to spend 3 slides on how to get those recordings with the D-Patch amplifier system, our new flagship model, the ultra-fast low-noise amplifier system. One of the features that you need for single channel recordings is low noise, is a good noise performance, and the D-Patch has a noise performance of less than 220 femtoamps in a 10 kilohertz bandwidth, which is well enough for good single-channel recordings. Here's an example of a recording that John Sack and co-workers did in Woods Hole earlier this year. This is a KV2 channel recorded from a cell-attached patch in this case. Just for completeness, the D-Patch also has current clamp capability with a dedicated head-stage circuitry that allows it, we call it fast follower, that allows it to act as a voltage follower with little distortion of the waveform to do action potential analysis. And another highlight is the high bandwidth. We have a bandwidth between 500 kilohertz and a megahertz, not quite a megahertz, and a sampling rate of up to 5 megahertz. So that makes it super fast. And one thing that I don't have on this slide, for those of you who have the opportunity to attend the Society for Neuroscience conference in Chicago, I think it starts on the 17th or 18th of October. Come visit our booth. We have just implemented and are putting the finishing touches on dynamic clamp capability for the D-Patch. So that might be interesting for some of you. Let me get to the talk proper, the single channel analysis with the Certipatch software. The workflow that we're going to follow is I will create a current amplitude histogram. We will talk about how to set levels, and we will detect transitions, and eventually, and that's what it's all about, a lot of science that we do is about the results. We are going to plot the results. 3 examples: duration distribution, amplitude distribution, and a scatter plot. The first step, the current amplitude histogram, also known as all points histogram, starts with looking at the data, and for that, let me quickly switch to Certipatch software. So here's a recording courtesy of Peter Prox at the University of Oxford in the UK. He gave us this data set to play with. This is a single channel recording. In this case, we have a single channel that is not quite constitutively open, but a lot more open than closed. If we zoom in far enough, we see individual transitions here, and most people would agree this looks like single channel recordings. And what we'll do, let me go back to the presentation here. What we'll do is create a current amplitude histogram over all points in the data set, all samples in essence. We'll do that by clicking on the current amplitude histogram. This creates a histogram like this, where we see 2 peaks, one for the open, one for the closed state, and then by fitting this with a second order Gauss function, we have 2 peaks in the Gauss curve. If a data set is as clean as this, they're clearly separated and everything. We determine the peak of the Gauss distributions, and that gives us the single channel amplitude, in this case 14.7, 14.8 picoamps. And we plug that into the transition controls, the amplitude, and in this case the recording starts with an open event, so the start level would be 1. And then as we hit the transitions, the software takes us from one transition to the next and lets us decide, do we want to accept, reject, or suppress them? And then we get an idealized trace. What we can also do is measure the RMS noise. In this case, we want to measure the noise of the closed state, obviously. The closed state noise is much lower than the open channel noise. And what we need to do is zoom in the portion that we want to measure the RMS noise for, and then as we hit the measure RMS button, the RMS noise is shown. In this case, it's a little under 400 femtoamps in this particular recording, which was recorded at a 20 kilohertz bandwidth. So this was a pretty decent recording, actually. So with the idealized trace, we create a number of plots. That's the third portion in our workflow. We start with the duration distribution plot. In essence, what that is the duration of the open channel events, and the frequency of particular durations is plotted. You can also make this a logarithmic x-axis and or a square root y-axis. This is in essence the same curve, only on a different scaling. Another common analysis method is the amplitude distribution plot, and in this case it's the open channel amplitude. This will be a Gauss fit of events from the idealized trace. Another common analysis is the scatter plot, and here we would see the peak current, the current amplitude, plotted versus the duration of the event. And you can apply limits, which hasn't been done in this case. You can set a minimum or maximum duration that you want to allow, and also you can constrain the amplitude that you want to look at. And again, this is for the open events. Last not least, since, as I mentioned, a lot of this is about the results, we can create a table of transitions. This is in essence the basis for the idealized trace that gives you one entry for each transition, and a table of the results where we look at the duration distribution, for example, and the plots. You have the parameters from the fits, etc., etc. This was a brief overview over the single channel analysis module that is new in Sutterpatch software as of version 2.03, the current release version. And let me finish with acknowledgements. This wouldn't have been possible without contributions from the DeepEdge hardware team, Rich Lobdill, who used to work with Axon Instruments as well, Aaron Best from Harvard Medical School originally, and Greg Yomstead, who worked at UCSF for many, many years before joining Sutter. The software team, Hubert Affolter, who came from Heka Electronic. Greg is also a member of the software team. Bert Mertz, who previously worked with Axon Instruments, and Telly Garatzatos, who came from Instrutech and Heka Electronic. And I would also like to thank Peter Prox at the University of Oxford for letting us use his single-channel data for this brief demonstration. And with that, let me switch over to the second presenter of the day, Angela Snyder. So you're on, and I'll go on mute.
Okay, thank you for bearing with me. So I'm going to talk to you about analysis of spontaneous excitatory and inhibitory postsynaptic currents and action potentials. So quick outline. I'll give you a very brief overview of my lab's research, how we record action potentials and spontaneous excitatory and spontaneous inhibitory postsynaptic currents, how to analyze action potentials using the analyze and the action potential analysis functions, and how to analyze the spontaneous excitatory and inhibitory postsynaptic currents using the event detection function in the software. The Silberman lab is an alcohol lab. We study how alcohol use and abuse affects neurocircuitry. I specifically focus on how alcohol and stress affect neurocircuitry in the limbic system using a mouse model. We do whole cell patch clamp recordings on neurons in rodent brain slices, so that will be data I will show you today. When we record action potentials, we record spontaneous firing without a holding current, or we do a current voltage paradigm. So there'll be no holding current at rest, and then we'll inject various current steps and observe the resulting membrane potential change and action potential firing. When recording these spontaneous excitatory and inhibitory postsynaptic currents in separate cells, we use antagonists in the ACSF. So for excitatory postsynaptic currents, we use picrotoxin, a GABA-A antagonist, and a potassium gluconate internal solution, and we hold at -70. For inhibitory postsynaptic currents, we use kynorenic acid, an ionotropic glutamate receptor antagonist, and we use a cesium chloride internal, and we also hold at -70. However, we are able to isolate these currents in one cell. So instead of using antagonists in this case, we change the holding potential. So we keep the same internal solution, potassium gluconate, and for excitatory, we hold at -55, and inhibitory, we hold at +10. How we apply this in the lab is we could compare the results across animals in different conditions, for example, a stress-exposed animal versus naive animal, or we could compare the results after applying a drug to the bath, so we could compare what is happening when the drug is applied to baseline measurements that we take. Before I go into how to analyze this data, I need to show you how to locate your data. So when you open your file, you'll click on Analyze Data in the dashboard right here, and then you will locate the series that you're interested in. So the data navigator pops up, and the data tree hierarchy will be the paradigm name, then the routine, and then the series. So when I refer to the series, this is what I'm talking about. For analyzing action potentials, I'll first talk about how to analyze the resting membrane potential and observe any possible rectification using the analyze function. As I mentioned before, we do input-output steps. We'll step from -100 picoamps to +140 picoamps in increments of 20, and then we measure the resulting voltage response. And as I mentioned, we can measure the resting membrane potential when we're not injecting current, the number of action potentials that result from each step, as well as the rectification. So after locating that series of interest in the data navigator, right-click and choose Analyze, and this is the window that will appear. Click on Measurements and Edit Measurements. And in this case, we'll change measurement 1. Our analysis function here is mean. The signal that we're analyzing is voltage. Our cursors will be relative to sweep time, and you can set the start and end time if you would like to change that. And then the y-axis in this case will be the mean voltage, and the x-axis will be the time with the unit of seconds. You can see here our measurement, and we set this, and you can actually manually move that if you'd like to. We'll click Run Analysis, and we get this output chart. One tip that I have is that when you click Run Analysis, if you don't see your plot appearing, it's likely popping up, but it's off screen, so you need to adjust the size of the window using the corner down here, and then it will bring it onto your screen. Then you can hit Save Analysis, and that will allow you to save it either as a graph or a table in the analysis editor. You can click on this scroll here to export it to a layout, or you can click on this copy icon here to copy the graph or the table. To check for rectification, this is an example of how we can use two different measurements. So we'll change the measurement settings to add another measurement ID, and then we change the Y and X axis to the desired labels. To check for rectification, we need some measurement for the voltage and then a measurement at the current. And here we have on the x-axis the mean voltage plotted, and on the y-axis the current steps. And since we do observe a curving of this plot, that indicates that there is rectification occurring. If we did not see any curve and it would be a straight line, that would indicate that no rectification is occurring. Now to analyze action potentials specifically using the action potential analysis function, you'll locate that series of interest, right-click, and choose action potential analysis, and this window will appear. Then you'll adjust the parameters to detect the specific action potentials within the trace. Some important parameters to watch are your threshold value, and this is the value that must be reached to be detected. So in order for us to count an event as an action potential, we need it to cross 0. So that's why our threshold is 0. APD stands for action potential duration at percent repolarization. Here we have it set to 50%, but you can change that to other percentages if that's what you're interested in. After clicking Start, you can click on this arrow in the corner, and you can view a phase plot as well as other measurements for each particular event. So this phase plot is another way to view the kinetics of an action potential. On the x-axis, you have voltage, and on the y-axis, you have the rate of membrane potential change in voltage per second. And how to read this for a threshold value is this point, and the peak value is around this point, and you have other measurements that are reported in this results table. And you can get this for each individual action potential. When you click Save Results, you generate a table that details each event and a layout file for the average event. While each of these column labels are pretty self-explanatory, all the definitions of each one can be found in the IPA and Sutterpatch user manual. Now, using the event detection function, we can analyze spontaneous, excitatory, and inhibitory postsynaptic currents. For excitatory postsynaptic currents, you'll locate your series in the Data Navigator, right-click, and choose Event Detection, and a similar window from before will appear. You'll next need to click Template and change the parameters to be about what you would expect your average event to be. For excitatory inward currents, the event polarity should be set to -1, and then you'll put your expected rise time and decay time and click Create Template. Another parameter to look out for is the threshold. The default threshold setting is 4. Higher numbers make it more likely that you'll miss events, but lower numbers make it more likely that you'll detect false events. We start with 1 when we have a very good trace, and then we check the fit from there. Once you have your template and you create your template and hit Start, it begins the search for all the events in the trace. Then we click Average, and then we check to see if the template fits well. In this case, we do have a very good fit. You are able to scroll through the events when you click in the event box by using your scroll wheel or clicking on the arrows, and we do this to make sure that all the events detected are real and that we're not missing any. You are able to also remove any false events if you need to. And then after hitting Average again, you can adjust your threshold, your amplitude threshold, and your template as needed. Once you find the ideal settings, use these settings for all traces of the same cell in order to remain consistent within your analysis. You'll click Save Results to generate a table and layout output. When you exit these windows, be sure to save because they are accessible later by clicking on the Windows menu at the top of the screen, and then either the table macros or layout macros for whichever you would like to access. The main outputs we use are the total event number and the average amplitude for each of our recordings. For inhibitory postsynaptic currents, the process is similar. You'll locate the series, right-click, click Event Detection. Immediately, we change the amplitude threshold and the event polarity because we expect our inhibitory events to be much larger. And in the way we're recording in this case, our inhibitory events are outward. So we need to change the event polarity to 1. Then again, you create your template, you hit Start and Average, and you'll get your average trace with the template around it. So in this case, the template's okay, but the event number is very high, so that's way higher than expected. And the average event trace is poor with this overshoot likely created by excess noise in the recording. And so this is because we've chosen a threshold of 1. So we likely need to change this in order to decrease false detections and make sure we're only detecting real events. So we ended up with 3.7 as our threshold in this case. So this is a much better fit. And by clicking through manually in this event box, we were able to verify that the correct events are detected and that we're not missing any real events. Again, you'll click Save Results to generate the table and the layout output, save these windows that you can access later. So overall, I explained how in our lab we record spontaneous excitatory and inhibitory postsynaptic currents, how you can do this in separate cells with antagonists or within one cell by just changing the holding potential. Explained how we record action potentials and different applications for these measurements within the lab, and how to do analysis of action potentials using the analyze and action potential analysis functions, as well as analysis of the spontaneous and inhibitory postsynaptic currents using the event detection. So thank you. This concludes my section of the webinar, and I'll be happy to take any questions at the conclusion of the entire webinar.
Thank you very much, Angela. That was a very nice talk, and I'm very pleased to hear that the Sutterpatch software is so useful for your workflow. And I hope that your presentation will help guide other users through a similar workflow. With that, let me make Telly the presenter.
I'd like to thank all of you also for attending my talk on the reality of virtual signals as it applies to the Sutterpatch software. So what exactly are virtual signals? Basically, they are mathematically transformed data. We take an input source, we apply some math to it, and the result is a new signal without any alterations to the original data set. Now, virtual signals can be generated during routine acquisition. So here we show the routine editor, and we have the input channel window open. And down in this section right here, we could define up to 10 virtual signals that will execute during routine acquisition. In addition, virtual signals can also be created, modified, or deleted during reanalysis procedures. So here in the scope window, we have the measurement menu. So we specify edit virtual signals. The edit virtual signal window will appear. As you notice, the controls are very similar to the ones in the routine editor, except for the additional do it and delete button, and those are used to actually process what we're trying to do. So now let's describe the math types that are available in Sutterpatch. So I've divided them down into 3 categories. So first are signals that provide or run some kind of filtering. Then we have sweep-based modifications, and finally, mathematical functions. All virtual signals require a source channel, which could be either an acquired signal or another virtual signal. And they also have optional scaling parameters. So both offset and factor can be used for each signal. So let's get started with a definition of them. In the first category, we start off with a smoothing filter. This is a moving average noise reduction filter, and it comes in 2 flavors. So the first is a Gaussian binomial. This is a standard filter. This has excellent 10 to 90% rise time response. The second is a boxcar, and this is a fast time domain filter, and this has excellent 0 to 100% rise time response. For the Gaussian, there's only one parameter that we need to set, and that's the number of smoothing operations. For the boxcar, there's 2 settings. The first, the number of repetitions, and the second is the number of points in the smoothing window. We have found that odd values provide the best performance. Another filter that is available as a virtual signal is a Bessel filter. So many of you know the Bessel filter is an analog linear filter. It's used in many electronic applications. And the reason for that is 2 characteristics. One is it preserves the wave shape signals with the pass band. And the other is the transition from the pass band to the stop band is shallower than other filters. And the digital version, or the software version, is a far more stable and predictable since it's not subject to the electronic component nonlinearities of analog filters. Now, the Bessel filter has a lot more parameters than we need to specify. So the first is the filter bandwidth, and that could be either a low pass or a high pass. So for low pass, all signal frequencies that are less than the specified cutoff cutoff frequency are included, and for high pass, all the signal frequencies that are greater than the cutoff frequency are included. The second parameter, filter order, or sometimes referred to as the number of poles, or in this case, the number of transfer functions. Simply put, the higher the number, the greater the precision and sharpness. And finally, the cutoff frequency. And this needs to be set to less than or equal to half the sampling frequency of our source channel. Now, there's an additional parameter settings in these two virtual signals that handle the integrated reset for the D-patch. Jan briefly talked about the D-patch. The D-patch has capacitive feedback mode. And with that, those capacitive integrator circuit needs to be reset. And during that reset, there are capacitive transients that are introduced. Now, some applications hide what they do with these transients. We give you a choice on what you can do with them. So if you do it as a virtual signal, you can then specify to either ignore it, which means that it will show the capacitive transients as they appear from the hardware. You could blank them, which means that you will replace them with NANDs, or finally, you can mask them, and masking them will take the last good data value and replace all those transients with that value. This is sometimes referred to as a sampling and hold operation. Finally, if you're using either the blank or the mask, then you also need to specify a duration that completely covers the transient duration. The next virtual signal I'd like to go into is line frequency reduction. So many of you have probably seen this kind of line noise before. AC power contains either 50 or 60 hertz oscillations that cause line frequency noise in recorded signals. I mean, those could be as simple as the sine wave we see here, or they could have very complex waveforms. Typically, there are two approaches for resolving this type of issue. The first approach, and I believe is the best approach, is to actually take the time to denoise the rig. But sometimes that doesn't take care of the job, and there's many environmental factors that could be a problem for that. So in those cases, you could use either a hardware or a software line frequency filter. Now, the hardware approach, sometimes referred to as a hum bug or a hum silencer, there's a lot of different names for it, take an input, go through some black box, and then give you an output. Well, the caveat here is what is actually happening in that black box, and that's really an unknown. For Solder Patch, we decided to take a different approach. So we came up with an FFT-based algorithm, and we find that it reduces the noise greater than 90% over 6 harmonics. And more importantly, the original signal is never altered in any way. There's only one parameter that we need to take care of for the line frequency reduction, and that is to set the line frequency of the region you're working in. Line frequency reduction, or should I say the line frequency reduction algorithm, is also available in the membrane test. So from the signal parameter section, we could enable either replace a signal or add a signal, which will then replace what is shown in the scope window. In this case, we said replace signal, so it took the data, it performed the algorithm, and then it shows the results. The next virtual signal I'd like to go into is the P/N leak subtraction. A cell's response to a voltage clamp stimulus can be roughly divided in two parts. The active changes due to the gating of the voltage-dependent channels, the passive response due to the membrane resistance and or capacitance. So P/N leak subtraction is a technique for canceling the passive components that may obscure the signal of interest, and this is the reason why I put this signal in the filtering group. Now, to use this virtual signal, there is a prerequisite, and the prerequisite is a stimulation where you have to create a leak pulse. And a leak pulse is a scaled replica of the stimulus waveform used to record a fraction of the leakage current, as shown here. So we do that in the routine editor in the output channels at waveform window. Once we enable the P/N leak pulses, it shows us a whole new set of controls and settings. I won't go into them as they're all described in the Solder Patch manual. For the virtual signal itself, there's only two settings that we need to specify, and one is show leak, which will display the accumulated currents in the scope window. And the other is to specify the leak zero segment. Now, that segment is a stimulus segment without any active cellular response. Typically, in the waveform editor, we have a segment that we could define as set to hold, and this is the segment that we're talking about. So what the algorithm does, it takes the second half of this segment data and computes an average leak current. This in turn is used to correct the P/N leak average. Now the benefit of this is that it reduces the influence of a constant leak current, which is otherwise added to the leak current of the main pulse. So here's an example from a user, Dr. Chris Leonard, who did the P/N subtraction. In this case, he didn't have a change in amplitude, but a change in duration. If you notice something here that's different from other applications is that we actually acquire and show the leak pulses, not just the results. So let's go into now the sweep modification virtual signals, and we'll start off with baseline subtract. So this also comes in a couple of different versions or flavors. The first one, the simplest, is value. So here we specify a fixed value, and that value is subtracted from the trace. The next one is trace, and here we compute the mean average and then use that value subtracted from the trace. Then we have two settings that are based on regions that we specify. So the first one is sweep time, and this computes the mean within the region specified by the start and end time, and then that value is subtracted. And then finally, we have segment-based, and segment-based computes the mean within the region specified by the source channel's parent output channel. So that is information that is stored in the routine copy and we have access to. And then again, here you can fine-tune the region by modifying the start and end ratio. Here's an example of a trace that had a slight shift in the baseline. And here we created a virtual signal during the reanalysis, and where we sweep and we specified a start and end time, which gave us a region somewhere in the beginning of that sweep. And here is the results after we executed it. So here on top of the scope window is the raw data, and on the bottom side is the new virtual signal. And here I just highlighted the area to show the change. The next virtual signal is sweep average. And again, sweep average comes in two flavors. You have either cumulative average or a run average. And with run average, you also need to specify the number of sweeps that are continuously averaged. Here is a quick movie of a cumulative average. And I showed this because you could see that as the running average is going through from sweep to sweep, the signal to noise is improving. Okay, the next virtual signal, again, it's a sweep modifier, a sweep subtract. Very simply, we specify a reference sweep, and then that reference sweep is subtracted from all the other sweeps. Quick note, during routine acquisition, if the sweep specified does not yet exist, no subtraction will occur. Finally, in this category is stimulus. There's many times where we need to have a copy of the stimulus template. This is an easy way to get back this waveform. So basically, here we had a current that we recorded, but we did not record the voltage that was associated with it. So we could just create a virtual signal with math type stimulus, and here we automatically get a new scope that shows us both the current and the stimulus that was used. A quick note, as Angela mentioned, you have the clipboard and layout buttons here as well to give you a quick layout. Brief note, I know this is a little bit out of context, but since it was talking about stimulus, the same information from the routine copy can also be retrieved during online analysis. So if you are only looking for segment amplitude or segment duration, instead of recording the entire trace or getting a virtual signal and then creating a measurement for it, you could just specify a segment amplitude as an analysis function, and then you could specify what output channel and what segment you want to get that information. In this case, we're doing an IV, so we had the current recorded, so we're able to get the measurement for that portion of the graph, and we got the information regarding the amplitude from the routine copy itself. Now let's go into virtual signals with math functions. So we could do integration, or we could do differentiation. And here we have an example of that. This one actually uses two virtual signals. So the first virtual signal is a smoothing of the voltage trace of the action potentials. And then the other one, the lower one, is actually a differentiation. In this case, it was used for real-time analysis to count the spikes to get a frequency. Next, talk about equations. So equations are actually not only used here, but equations are used throughout the routine editor. They're used in the paradigm editor. They're used for all sorts of online analysis. They're used throughout Sutterpatch. And as Jan mentioned, we also use them quite heavily in the dynamic clamp editor in our new dynamic clamp development. This uses a common window, so depending on how it's used throughout the program, the window is always the same. You have different choices of special identifiers. So here you could specify the equation, you could check the equation, and you could undo those changes. An example that I use for virtual channels, something that was requested by a user, and what they wanted to do was to subtract the data of one series from another to isolate a drug-sensitive change. So this is a series operation. So here, the formula that we used, or the equation that we used, is first as we went to the data navigator and we selected the current series that we want to work with. So that's our S0, 0, 1. And then we subtracted that from the previous series. And that's why we do -1, which means the previous series with the same parameters for sweep counter and signal number. And basically, the results would give you a new virtual signal with one series subtracted from the other, sweep by sweep. And the final virtual signal that I like to talk about is a lock-in. And this one I'm just going to go over briefly. I mean, to actually give it really justice, it requires a webinar on its own. So I'll just give you a quick overview of it. This is for capacitance measurements. And so during a voltage clamp recording, a stimulus, in this case, which includes a sine wave voltage, is used to record the current response. Now, the resulting current plus the computed holding current is used to calculate the various lock-in parameters of the three-state model. Now, all of these calculations and techniques are outlined in the following publications. I won't go into detail, but they're all available online for your review. Just like the P over N leak subtraction, the lock-in also has a prerequisite. As the description stated earlier, we need to have a segment which is a sine wave voltage. So here, this is actually created in the waveform editor section of the routine editor that would allow us to define the sine wave and the cycle. For the actual lock-in parameters, there's a number of settings that need to be set. The first one would be trace kind. So we have choices there. The first one is we could get a overview of the computed membrane capacitance. We could get the computed membrane conductance, the series conductance, the DC component of the measured signal, the real part of the lock-in response signal, and finally the imaginary part of the lock-in response signal. We could also specify the cycles to average and cycles to skip. And the final parameter, which is quite important, is the V reversal. And this needs to be the reversal potential of the dominant ionic current. Please note that it's also specified in the papers, but the holding and the reversing potential need to be sufficiently different to achieve reasonable results. Here's an example of a lock-in from a user application. Here they had two lock-in segments, one before the pulses and one after, and then they used the online measurements to basically subtract and get the change in membrane capacitance. And finally, the lock-in is also available in the membrane test. So the same way as the line frequency reduction is, you could specify a lock-in cycle, and then it will send out a sine wave, and then the computations for membrane capacitance and membrane resistance are all done using the lock-in calculations and not the formulas used in the membrane test equations. Finally, the virtual signals, like the other methods that were described today by Angela and by Jan, is just another powerful tool that's available to you from Sutterpatch. And like our trusty Swiss Army knife, Sutterpatch provides a number of tools for analysis, for stimulation, for graphing. It's a very powerful tool that you could use to help your workflow. And with that, I would like to open up the question and answer session of this. Thank you.
Thank you very much, Jelly, for another instructive talk. And it looks like we have a number of questions from the audience already. You said you were going to host the Q&A session, right?
Yes, there seems to be a number of questions. So first one looks like it's for you, Jan. Is the raw data file format compatible with Axon analysis software and Heka software?
The raw data file format is an Igor experiment. We implemented an export functionality. You can export the data in ABF, the Axon binary format. That is not only compatible with Axon software, but also a lot of third-party applications. And that's who we originally implemented that for. People who use, some people use MATLAB or other third-party software that reads ABF format just because it's a very common format. For the Heka format, no, we do not allow you to export the data directly to the Heka file format. But then most people who acquire their data with Heka a lot of people would use Igor Pro, which Sudderpatch is based on for their analysis anyway, or some other third-party software. And Igor has a lot of export formats, and you can export in several binary or text-based formats.
Great, thank you. So here's a question for you, Angela. For the analysis of minis, is there an option for your analysis software to learn the template of minis from real events pointed by the operator? Is there an option to use both threshold and template modes combined during the analysis of minis? And that's a long question.
Okay, so for the first part of the question, please correct me if I'm wrong, but I don't know of any way for it to just learn a template by selecting real events. However, if you take a shorter duration recording, you can delete the false events and keep only the real events in the trace. And then taking the average of that, you can determine your template. And then that template's saved for the rest of your analysis unless you change it, or at least write that down for each cell you analyze so you could go back and put in the correct parameters. And another option is to locate one real event in a trace and change the template based on that one event if that's what you'd like to do, but that tends to be pretty different than an average template. And then in terms of the threshold and template modes, if I'm understanding your question correctly, I might not have made that clear, but it's using both of your settings for detecting your response. So you can set your threshold and you're setting your template, and it's using those in combination when detecting the minis or the response. You can deselect the amplitude threshold function, but typically I do select that. So then all that information in combination is used when detecting the events.
Yeah, I mean, one more comment from me on that is I will also reach out to our colleague Greg, who wrote all of the event detection software, and see what he says. Unless Jan, you may know a better answer as well.
Not an answer, but what I was going to say, in essence, it's a very good suggestion to make, in essence, the template dependent on a past analysis, and that has been suggested at least once before, so this is the second time. And of course, we are open for all requests and suggestions from users, and that means we will see whether we can implement that. It's a good idea, and we'll look into that definitely. At this point, Angela is perfectly right. At this point, it's not possible.
Okay, here's a question that I will tackle. Sudderpatch software, what about online acquisition, analysis versus the possibility of using software for offline analysis? Number of licenses locked to a single computer. Let's start off at the beginning. So both virtual signals can be executed during routine acquisition. So when you're acquiring the data, the real data is first acquired, and then the virtual signal is created within that sweep before the next sweep is executed. So all the virtual signals will run in real time during the acquisition. That's also the case for the online measurements. So any of the online measurement graphs and measurements that we have available will also occur either real time during the acquisition or offline. As for number of licenses, so an Igor license allows you to have two running systems, one usually on your acquisition setup and one for analysis, and so we follow the Igor license on that. So it's not locked to a single computer. For the single channel analysis, there's actually plans to add a couple so-called quick analysis measurements to the real-time analysis, but that will come, I can't say exactly when that is scheduled for. Here's another question for you, Jan. Are you planning any further analysis functions or features for single channel analysis?
Yes, absolutely. What we have implemented in the current release version is a first stab at a somewhat basic single channel analysis. And at this point, we could go a variety of ways. So we are very open for user input, user suggestions, as I mentioned, in which direction we should go and how to prioritize our development bandwidth. And as we have done in the past, we will continue developing SudderPatch software, and a lot of times we have done that based on user requests. The ZAP function, for instance, is one example, or a feature that we would have added much later had it not been for a user who requested it. And we have a number of cases where something was either based on user input to begin with or has been prioritized based on user requests. So feel free to let us know what you need, and we can prioritize our efforts in that direction. We are very open and welcome input.
So Angela, here's one for you. What criteria do you look for when determining the proper threshold and template when measuring the spontaneous potentials?
Okay, so when I do that, I look for first the shape of the event. You want it to have that characteristic shape with the correct rise time and decay time. So again, the rise time and decay time are important. And I also really make sure that we're not detecting any false events or missing events. So doing that, I would go through manually and just be sure that it's actually being accurate. And then if it's detecting too many false events, that's when I would change that one threshold number. And it's sort of a educated guess / trial and error initially until you understand how your recordings are going to come out.
Great, thank you. Here's another question. Have you, and this, I guess I'll tackle this one. Have you thought about integrating or perhaps more correctly synchronizing ePhys data with imaging data when SudderPatch is used in experiments and combine ePhys recording and imaging, for example, 2-photon imaging? It can often be tricky to keep track of which data goes with what. Yes, we have, and yes, it's scheduled to be a development that will occur. Now, again, I'm not sure what the timeline is, but you're familiar that Sutter does have 2-photon imaging, and we have expertise in both sides, so I think we're going to make this work. Our goal in the next few releases is to also integrate more and more of the Sutter product line into SudderPatch, for example, the light sources being one of them. Stay tuned for that. There's one more question here for Jan. Does single channel analysis support multiple open channels?
Yes, you can have multiple levels, but of course, the more channel copies you have in your recording, the more questionable the results can become. And some people even say if you have more than one channel copy in your patch, you're not doing science. But I'm not going to comment on that, but let the people bash their heads in individually. I just saw one more question that I think is an excellent question, so I would like to address that during the session, if you don't mind. The question is whether we need to use the same head stage for both voltage and current clamp in the D-patch. And the answer is yes, you can use the same head stage. The D-patch comes with either one or two head stages, and they are completely identical in their functionality. And you can use one in voltage clamp, the other one in current clamp, or totally independently. Each head stage has 3 feedback ranges, 2 resistive and 1 capacitive range. And the capacitive range cannot be used in current clamp, obviously. You would have to use one of the 2 resistive ranges. But other than that, each of them can be used for both modes. And there's dedicated voltage follower, fast follower circuitry in each head stage.
Well, I'd also like to add one more point to that, that the IPA only has a single resistive feedback mode, but it also supports both current clamp and voltage clamp experiments with a single head stage.
That's correct, yes. Good point. And I think with that, we should leave the session open if somebody wants to type more questions that we will address offline by email, but stop the audio, and in 4 to 5 minutes or so, we will close the webinar. Thank you very much, everybody, for attending today and for all the questions you asked, and stay tuned for the notification when the recording is available online on our YouTube channel. Our YouTube channel, by the way, also has a lot of other useful resources available. Thank you very much, and goodbye.
Explore our YouTube channel to find our latest support videos and product announcements. Subscribe now.